Okay, we're now in section 4.2, and in section 4.2 we have two very important theorems. Well, actually one important theorem. Rolle's theorem is a subset of the mean value theorem. But we start with Rolle's theorem because it's pretty easy to understand first. And Rolle's theorem says that if y equals f of x is continuous at every point of the closed interval a to b and differentiable at every point of its interior a to b, then if f of a equals f of b, there's at least one number c in which the derivative f prime of c is 0. And the picture makes that really easy to understand, right? So I have an interval from a to b, have a nice, in this case, a picture of an upside down parabola, really easy to get a picture of in your mind. And notice that f of a is equal to f of b, right? At the two endpoints, the function is equal. So if I draw a line through them, notice that the slope of that line is 0 because it's a horizontal line because f of a and f of b are equal. That means that somewhere between a and b, there's at least one value of c where the derivative is 0 also, right? Because to get from here over to here and end up at the same value, as long as the function is continuous, it had to go up and then come back down, which means I have a maximum, in this case, where the derivative would be 0. This is a picture of showing you that we just have to know that at least one value of c in that case, because here I have an interval from a to b where the function at a is equal to the function at b, so I have a horizontal line that connects those two if I want. In this case, I actually have three different values of c, c1, c2, and c3 in this picture where I have a horizontal tangent line. So that's Rolle's theorem. The mean value theorem extends that idea, and again, this is just telling you that it doesn't work for discontinuous functions or where functions have a derivative that doesn't exist. You can't necessarily say it. So the mean value theorem says, well, let's don't force f of a and f of b to be equal, but let's say f of a is this value right here, f of b is this value. Then if I connect those two with a line, then somewhere between a and b there's some value of x, call it c, such that the slope of the tangent line at that point is the same as the slope of the line connecting f of a and f of b, right? Because the slope of that line is f of b minus f of a over b minus a, change in y over change in x. That would mean that the slope from this picture we can see has to be the same value as that slope. In other words, f prime of c equals f of b minus f of a over b minus a. Of course, that's true only if f of x is continuous again and differentiable on the inside as well of the interval a to b. All right, so those are the ideas. We have a couple corollaries that go along with those. If f prime of x equals 0 at each point x of an open interval, then f of x has to be a constant, because if f prime of x equals 0, we know that the function has to be a constant for all x, right? Because f of a equals f of b everywhere in there. They're always the constant. And if I have f prime of x equal to g prime of x at each point in an open interval, then that means there is only a difference between the two functions of a constant. Because notice if I take the derivative here, f prime of x equals g prime of x plus the derivative of a constant, which is 0. So if the derivative of one function is equal to the derivative function everywhere in an open interval, then the only way these two functions can be different is by a constant. Okay, so we want to use, in this example 56, the intermediate value theorem. So the intermediate value theorem was not in this section, we had that before. The intermediate value theorem says that if I want to be on the interval a to b, if I get from f of a to f of b, then there has to be some value between a and b, some value of x between a and b, such that that value x, let's call it c, f of c is equal to some value between f of a and f of b, right? I can't get from f of a to f of b without crossing that value, as long as f is continuous. So that's the intermediate value theorem. So we want to use that and Rolle's theorem to show that the equation x cubed plus 3x plus 1 equals 0 has exactly one real solution. So considering that function, we note a couple things. So what you have to do is, I want to show there's only one real solution. So at least find a value where it's negative and a value where it's positive, okay? So if you notice real quick, f of minus 1 ends up being minus 3, which is a negative value. F of 0 is 1, which is a positive value. So that between x equals minus 1 and x equals 0, this function has to cross the x-axis somewhere to get from a negative y value to a positive y value. Okay? So if there were 2, though, then that x equals a and x equals b such that f of a and f of b were 0, then Rolle's theorem would say there's at least one such that f prime of c equals 0. But f prime of x in this case, notice f prime of x is 3x squared plus 3, which is always a positive number. That means that f always has a positive tangent line, always has a positive sloping tangent line, which means that it's constantly increasing. It can't come back down. So f of x only has 1 0. That's the end of example 56.